Warm greetings to all. Today we are going to discuss about the stability of the control system. For the system what we have designed, our aim is to make the system a stable one. And whenever if we are in a purpose to change any factor of the system, we have to see that the stability of the system does not get affected. So today we are going to see how we are going to analyze the stability of the system and how we are going to change the stability of the system. So stability of the control system is the concept what we are going to discuss now. And stability of the control system, it involves two concepts. One is the bounded input, bounded output stability, that is the BIBO stability. And the another concept is the zero input stability. The first concept, bounded input, bounded output stability, states that whenever the input is within a bounded region, the output should also be in a bounded region. That is, the output should be a finite one in order for the system to be a stable one. And this stability analysis involves three methods. They are the Routh locus method, Routh Hurwitz criterion method, and the last one is the Nyquist plot, that is the Nyquist stability criterion. Among this, the first one, Routh locus methods, involves the time domain analysis of the system, and this process is a complex one and it involves many complex steps. The next two, the Routh Hurwitz criterion and the Nyquist stability criterion, are the frequency domain analysis method, whereas this Routh Hurwitz criterion determines the absolute stability of the system. And the next one, Nyquist plot, determines the absolute stability and also the location of poles of the system. And today we are going to discuss about the Routh Hurwitz criterion. And in this Routh Hurwitz criterion, we are going to discuss about the bounded input, bounded stability. That is how this concept is being used to determine the stability of the system. And first, initially, Hurwitz determined that by forming a determinant using the characteristic equation of this system, we can determine the stability of the system. And afterwards, Routh determined that determinant can be reduced to a smaller array, and so that the stability of the system can be found using a simpler method. And in this stability, we are going to see the control system. First, actually, what a control system? Let me take a control system with input C of S, which is the, let me take an input R of S, which is the reference input, given to a system with transfer function G of S. This system may be any plant and its output is given by a control, it's a control output, so C of S, and a feedback which senses the changes in the output with the transfer function H of S. And the transfer function of this system is given by this whole system is given by T of S is equal to G of S divided by 1 plus G of S into H of S. As this is a negative feedback system, transfer function has been derived as G of S divided by 1 plus G of S into H of S. And this denominator equation, which is 1 plus G of S into H of S equal to 0, is the characteristic equation of the system. And this characteristic equation is going to play an important role in determining the stability of the system. And this characteristic equation will be a polynomial equation in terms of S. Let me consider a polynomial equation to the power a1 to the power s power 5, a2 s power 4 and a3 s cube plus a2 s power 2 a4 s power 2 a5 s power 1 plus a6 s power 0. That is, this equation is nothing but a1 s power 5 plus a2 s power 4 plus a3 s power 3 plus a4 s square plus a5 s plus a6 s is equal to 0. And how we are going to form the Routh array with this equation? That is what we are going to determine the stability from this equation. Before going into it, we have to see an important concept about the stability. And when we are determining the characteristic equation of the system, if the roots of this characteristic equation lies on the left half of the S-plane, if all the roots of this characteristic equation lies on the left half of the S-plane, then the system is said to be a stable one. That is, whenever the roots of this characteristic equation lies on the left half, this system is said to produce a stable output and the system is said to be a stable system. Whenever the roots of this characteristic equation comes to the right half, the system is an unstable system. And let us see how we are to form the Routh array for this system. Since it is coming from the power s power 5 and s power 5 is an odd number, so let us take the coefficients of all odd powers of s. So a1, a3, a5, and the next one is s power 4. It has been taken as an even number and all the coefficients of even powers of s are taken. So a2, a4 and a6. And the next row of the array is to be formed. Let me consider the next row as b1 and b2, where this b1 is given by the equation a2 into a3 minus a1 into a4 divided by a2. This is the equation of b1. And the next one, b2, is given by the equation b2 is equal to a2 into a5 minus a1 into a6 divided by a2. That is, a2 into a5 minus a1 into a6 divided by a2. This is the equation for b2. Then again the next row is being formed for s power 2. That let me consider the elements as c1 and c2, and the elements has been given as c1 is equal to b1 into a4 minus a2 into b2, b1 into a4 minus a2 into b2 divided by b1. This is the element for c1, and the next element c2 is given as same way b1 into a6 minus a2 into 0. b1 into a6 minus a2, since there is no element we are considering here as 0, so a2 into 0 divided by b1. This is the element c2. Let me consider for the next row s power 1. Let me consider the elements for this row as d1. So the element d1 is given as c1 into b2 minus b1 into c2 divided by c1. That is, d1 value is given as c1 into b2 minus c2 into b1 divided by c1. This is the element for this row d power 1, and again this row has to be reduced to s power 0. Let me consider the element as s power 0's element as e, and this element e is given by the equation d1 into c2 minus c1 into 0 divided by d1. That is, d1 into c2 minus c1 into 0 divided by d1, which implies that this element is c2. So this is the Routh array which we are formed with this characteristic equation, and here we are having three cases. That is, when we are investigating this Routh array, if all the elements of this first column of the Routh array are positive, if all the elements of this first column of the Routh array are positive, then the system is said to be a stable system. Whenever there is a sign change in this first column of the Routh array, the system is said to be an unstable system, and the number of sign changes is said to be equal to the number of roots on the right half of the S-plane. As I have said you earlier, whenever the roots are going to lie on the right half of the S-plane, the system will be an unstable system. So as it is, whenever there is a sign change in the first column of this Routh array, the system is said to be an unstable system, and the number of sign changes is equal to the number of poles on the right half of the S-plane. So let us see some examples for each and every case of this Routh array. So let me consider a system. Let me consider a system with transfer function with the input R of S. Let me consider a unity feedback system with the transfer function 1000 divided by S plus 2 into S plus 3 into S plus 5. This is the transfer function of the plant which we have designed, and let the controlled output be C of S, and let the plant be sensed by a sensor of feedback H is equal to 1. This is considered to be an unity feedback system, hence the transfer function at the feedback is given as 1, and this has been taken as a feedback and given as a negative feedback, and for this system we have to find the transfer function. So in order to find the transfer function, what is our formula? Our formula is given by T of S is equal to G of S divided by 1 plus G of S into H of S, which is equal to 1000 divided by S plus 2 into S plus 3 into S plus 5 divided by 1 plus 1000 by S plus 2 into S plus 3 into S plus 5. So by taking the LCM and cancelling the denominators, 1000 divided by S plus 2 into S plus 3 into S plus 5 plus 1000, which is equal to 1000 divided by S square plus 5S plus 6 into S plus 5 plus 1000. This is our transfer function. Again, by reducing the transfer function, we will be getting 1000 divided by S cube plus 25S plus 6, plus 25 S cube plus 25S plus 6S plus 30. So this equation has to be reduced further in order to find the characteristic equation. So T of S is equal to 1000 divided by S cube plus 5S square plus 6S plus 5S square plus 25S plus 30 plus 1000. That is 1000 divided by S cube plus 10S square plus 31S plus 1030. This is our transfer function. And from this transfer function, what is our characteristic equation? Our characteristic equation is the denominator of this transfer function. So the characteristic equation of this system is given by S cube plus 10S square plus 31S plus 1030 is equal to 0. This is the characteristic equation of the system, and this equation has to be taken into analysis and form a Routh array with the help of this equation, and we are going to determine the stability of this given system. So let me form the Routh array for this characteristic equation. So what is the power of highest power of S in this characteristic equation? The highest power of S is S cube. So let me form an array with the row, first row is S cube. Since 3 is an odd number, we are going to take into account the odd powers of S, that is the coefficients of odd powers of S. So S cube is 1 and S is 31, and the next row is with S square, and we are going to take into account the even powers of the S, that is the coefficients of even powers of S. So S square is equal to 10 and 1030, and we are going to form the next row S1, and S1, the elements of S1 are given by, let me take it as A1, that is A1 is equal to 10 into 31 minus 1030 divided by 10, that is 310 minus 1030 divided by 10, which is equal to 720 divided by 10, which is equal to 72, that is minus 720 divided by 10, which is equal to minus 72. Our A1 value is minus, so let me replace this A1 value with minus 72. So let me go to the next row, S power 0, which is going to be given by this equation. Let me consider this as B1, and this B1 value is given as minus 72 into 1030 minus 10 into 0 divided by minus 72, which is given by B1 is equal to 1030. So let me replace this value of B1 by 1030. So this is the Routh array which we have formed for this characteristic equation, and when we are analyzing this Routh array, we can see that there is a sign change in this Routh array, that is from this S power 1 row it changes from positive to negative, and here it again changes from negative to positive. Hence, how many sign changes are there? There are 2 sign changes. Whenever there is a sign change, 2 sign changes are there, which indicates that the system is an unstable system. And also we know that the number of sign changes is equal to the number of roots on the right half. Hence there are 2 roots lie on the right half of the S-plane. The 2 roots of this characteristic equation lies on the right half of the S-plane and make this system an unstable system. So let us see some other example where the roots are going to lie on the imaginary axis. Whenever the roots lie on the imaginary axis of the S-plane, this is our real axis, x-axis is our real axis, and the imaginary axis is j omega. Whenever the roots lie on this imaginary axis, the system is said to be neither a stable system nor an unstable system. So let us see an example for this. Consider a system. Again, let me consider directly the characteristic equation instead of going with the block diagram. Let me consider a system with the characteristic equation S power 6 plus 2 S power 5 plus 8 S power 4 plus 12 S cube plus 16 S square plus 16 S plus 20 equal to 0. So let me consider an example with the characteristic equation S power 6 plus 2 S power 5 plus 8 S power 4 plus 12 S cube plus 20 S square plus 16 S plus 16 equal to 0. With this characteristic equation, let me consider the system is a stable one or an unstable one. So let me form the Routh array. The first row will be S power 6. Since 6 is an even number, let me consider the coefficients of even powers of S. So it will be 1, 8, 20, 16, and the next row will be S power 15, which will be 2, 12, 16. 2, 12, 16. And when we are seeing this one, this array, we can see that there is a common factor 2 in this, all these 3 rows. So let me make it as 1, 6 and 8. So our new Routh array will be s power 6, 1, 8, 20, 16 and s power 5 will be 1, 6 and 8. This is our new array. So let me construct the next row of this array. And s power 4 is given by 1 into 8 minus 1 into 6 minus 1 into 6 divided by 1, which is given by 2. So let me replace this with 2. And the next element is given by 1 into 20 minus 1 into 8 divided by 1, which is given by 1 into 20 is 20 minus 8, which is 12. So this one is 12. And the next element is given by 1 into 16 minus 1 into 0 divided by 1, which is nothing but 16. So this is the next row of this Routh array. Again we are finding that there is a common factor 2 in all these 3 elements. So let me replace it with their common multiples, that is 1, 6 and 8. So our new Routh array will be 1, 6 and 8. So let me construct the next row of this Routh array, which is given by 1 into 6 minus 1 into 6 divided by 1. 1 into 6 minus 1 into 6 divided by 1, which is 0. And the next element is 1 into 8 minus 1 into 8 divided by 1, which is again 0. So we are finding a row of zeros here. Whenever we are finding a row of zeros, then there is a possibility there are some roots of characteristic equation lies on the imaginary axis. So we have to construct a row with non-zero elements. So for constructing that row, we are taking into account this s power 4 row, which is 1, 6 and 8. Let me consider this as A, which is given by s power 4, plus the next element will be s square and this will be a constant element. So s power 4 plus 6 s square plus 8. So we have to differentiate this equation as with respect to s. So dA by ds will be equal to 4s cube plus 12s, and the factors will be 4 and 12, and this is the s power 3 row. And again we are seeing that there is a common factor for these two elements, which is 4. So it is given by 1 and this is 3. So let the next element S3 will be, instead of the 0, we will be forming this row as 1 and 3. So again we have to form the next row. So S square row. So before that I will be taking into account the S3 row, which is 1 and 3. And the s power 4 row, which is 1, 6 and 8. So what are the elements of s square? The first element is given by 1 into 6 minus 1 into 3 divided by 1. It is 1 into 6 minus 1 into 3 divided by 1, which is 6 minus 3, that is equal to 3. So let me replace this with 3. And the next element is given by 1 into 8 minus 1 into 0 divided by 1, which is 8. So this is 8. So we are going to construct the next row of the Routh array. So the next row is given by 3 into 3 minus 1 into 8 minus 1 into 8 divided by this one, that is 3. So it is given by 9 minus 8 by 3, which is 1 by 3. And that 1 by 3 is equal to 0.33. This is the s power 1. So the last row of the Routh array is constructed as s power 0. It is given by 0.33 into 8 minus 3 into 0 divided by 0.33. That is, this value will be equal to 8. So the s power 0 row will consist of 8. So while we are analyzing this first row of this Routh array, we are finding no, there is a no sign change, but there is a row of all elements as 0. This row of all elements as 0 indicates that the system is neither stable nor unstable. We cannot say the system is neither stable system nor it is an unstable system. We can indirectly specify that the system is marginally stable. And also here we can find those roots which make this system a marginally stable system. That is, the roots, those roots on the imaginary axis can be found in this problem. How we are going to find those roots on the imaginary axis? So for finding those roots on the imaginary axis, let me consider the row at which this Routh array has become 0. At this s power 4 row, it makes the Routh array to be a 0. So let me consider this equation s power 4 plus 6s square plus 8 equal to 0. This is the equation at that particular row s power 4, and this has to be solved in order to find those 4 roots which lie on the imaginary axis, at which row the Routh array becomes 0, and that power gives the number of roots on the imaginary axis. So let me solve this equation in order to find the roots on the imaginary axis. Since we cannot solve it, we can consider s square is equal to x, and this equation will become x square plus 6x plus 8 equal to 0. On solving this, x is equal to minus 6 plus or minus b square, that is 36, minus 4 into 1 into 8, 4ac, that is 4 into 1 into 8 divided by 2 into 1, that is 2a. The equation for any polynomial equation is given by minus b plus or minus root of b square minus 4ac by 2a. And by substituting those elements in this equation, we find that x is equal to minus 6 plus or minus root of 36 minus 32 divided by 2, which is equal to minus 6 plus or minus root 4 divided by 2, which is equal to minus 6 plus or minus 2 by 2, which is equal to minus 6 plus 2 by 2, or minus 6 minus 2 by 2. And hence the roots is x is equal to minus 4 by 2, which is equal to minus 2, minus 8 by 2, which is equal to minus 4. So x is equal to minus 2 or minus 4. And by substituting x is equal to s square, hence s square will be equal to either equal to minus 2 or s square will be equal to minus 4. By solving this, s is equal to root of minus 2 or s is equal to root of minus 4, that is equal to s is equal to plus or minus root 2j or s is equal to plus or minus 2j. These 4 roots are those roots which lie on the imaginary axis, and these 4 roots makes this system to be a marginally stable system. So இன்னொரு எக்ஸாம்பிள் கொஞ்சம் கழிச்சு எடுக்கிறேன். ஸோ அப்படியே கண்டினியூஸாக எடுக்கணுமா இல்லாட்டி வேறு யாரும் எடுக்கலாம்? நான் தானா? ஆமாங்க சார். நேற்று இந்த ரேட் தான் சார் வந்தோம். Let me consider one more example for this Routh array. Let me consider the characteristic equation of a system to be s power 6 plus s power 5 plus 2s power 4 plus 2s cube, sorry 2s square. So Let me consider another example in which the first element, if the first element of Routh array is alone is 0, what is going to happen? So let me consider another system with the example. There is a characteristic equation to be s power 5 plus s power 4 plus 2s cube plus 2s square plus 3s plus 5 equal to 0. So let me construct the Routh array for this system, which is given by s power 5, 1, 2, that is the odd coefficients of odd powers of s, 1, 2 and 3. So the next row will be s power 4, which will be 1, the coefficients of even powers of s. So 1, 2 and 5. So the next row s power 3 is constructed as we have seen before, 1 into 2 minus 1 into 2 divided by 1, which is given by, which when we are solving leads to the value of 0. And the next element will be 1 into 3 minus 1 into 5 divided by 1, which again leads to the value minus 2. And when if we are proceeding this problem with this 0, it leads to the complexity. So we are going to consider this element 0 as some other constant epsilon, and let us proceed the problem. So s square, when it is solved for the next row, it will be 2 epsilon minus of minus 2 divided by epsilon, which will be 2 epsilon plus 2 by epsilon. And the next element is epsilon into 5 divided by epsilon, which is gives as 5. And we are going to construct again the next row, which is s power 1. It is given by 2 epsilon plus 2 by epsilon into minus 2 minus 5 epsilon divided by again this coefficient 2 epsilon by 2 by epsilon. On solving this, we will be getting 2 epsilon plus 2 into minus 2 by minus 2 minus 5 epsilon square by 2 epsilon plus 2, that is minus 2 epsilon minus 4 minus 5 epsilon square by 2 epsilon plus 2, which can be written as, by taking this minus sign outside, it can be written as minus of 5 epsilon square plus 2 epsilon plus 4 divided by 2 epsilon plus 2. This is our element which has to come here. So let me replace this element with that value, that is minus of 5 epsilon square plus 2 epsilon plus 4 divided by 2 epsilon plus 2. And the next element doesn't comes. So the next row of the Routh array, which is s power 0, that is the final row, is given by this element into this minus 2 epsilon plus 2 by epsilon into 0 divided by this element. That is, let me consider this as x. So 5x minus 0 divided by x, which again leads to the value 5. So this is our Routh array, and before analyzing this Routh array, we have to substitute that value of epsilon to be 0 in this Routh array. By substituting that value as 0, our Routh array is formed as the first row and the second row remains as it is, as 1, 2, 3 and 1, 2, 5, whereas this s power 3, by substituting this epsilon value as 0, because we have that value is 0, so we have assumed this as epsilon and we have proceeded till the last step. Now we are going to substitute that value. So s power 3 as 0 minus 2, then s square, when it is given as 0, 2 by 0, that is infinity, again 5, then again the next element will be minus 4 by 2, s power 1 will be epsilon is 0, here also 0, so minus 4 by 2, which is minus 2, and the last element is 5. While analyzing this Routh array, we have found that there is a sign change from plus to minus and from minus to plus. This sign change, there are two sign changes. This sign change, as I said before, the sign change itself indicates that the system is an unstable system, and this two sign changes again indicates that two roots lie on the right half of the S-plane, which makes this system an unstable system. So these two roots are to be corrected, are to be changed, or these are the factors to be changed in order to make this system a stable system. And with this, all these three cases has been discussed with this Routh-Hurwitz array. And these are the three cases which we have discussed till now. That is a system to be found for normal Routh array, and in which a Routh array of all rows is, all the elements of the row is 0 and the first element alone as 0. And these are the three cases to be discussed in the Routh-Hurwitz criterion. And with this I end up this session.